Hello everyone and welcome back to my channel. Alright, so I've got a few interesting things that have come up. Actually, I'm just going to move the camera over here for a moment. I really should have done this the other way around. Didn't think this through. Yeah, that's going to block the camera. Damn. Alright, that's okay. I'll just clip my phone here. I can stay there. Got enough space. Yep. Okay. Alright. You guys can still see. Right. I'm just going to draw this out, and I'll get a pen instead of a pencil so that you can see, because pencil just, with my messy writing and pencil, the two don't go hand in hand. Let me say that. If I don't draw this out, it's not going to make sense, and I've come to realise something. I've got a very bad habit, excuse me, of just holding the phone in something and saying what I'm doing, but I don't know that everyone can actually clearly see inside the actual circuit layout or the diagram, so to speak. And I don't want people to not understand what's going on. So the particular section I'm talking about, let's just set up a typical series pass element, NPN. Sorry, like I said, my writing is really messy. Anyway, now actually that's already a lie. This is getting driven from the positive off the cap bank. Just forget that line exists. There's also a separate positive rail that comes from a 2 transistor Zener regulator that goes to a 47k resistor that goes to a 1k resistor to the base of that transistor. The midpoint of this, the end of the 47k resistor, that goes to the collector of another transistor. Its emitter looks at the negative output. Just to be clear, this comes from the negative of the cap bank, positive cap, positive regulated supply. It's about 38 volts. This can go, it can be a multitude of different voltages. It depends what the tap is on the transformer. Okay, the base is basically, let's just put a box here and call it ref. And let's just say it's got a pot coming out of it. To adjust it, the reference is in between the base of this transistor, which is acting as a comparator obviously, and the output. And the way you set the voltage is by setting the reference voltage. So the negative of the reference is going into what normally would be a positive voltage, and the positive of the reference is hooked up to the positive out of the supply. That says sense and sense. If you can't, I don't know if you can read my writing or not. Right, that's better. Okay, so that might make a little bit more sense. So you understand just the basic topology, and then yes, this reference is powered from another regulated supply. It's a boost converter. It's the one that's underneath this main well switcher. Okay. Yeah, like I said, there's a regulator here. All right, so this is also a 4-stack up Darlington, but just, you know, to put it in simple terms, we just imagine it as one transistor. In reality, there's 4 there, and there's base to emitter resistors and base resistors and protection diodes and other things in there, but this is just a crude block diagram of the constant voltage circuitry. Incidentally, everything is thermally stabilized except for the comparator transistor. That's why I want to ovenize it. And the reason I'm trying to use a transistor, if you're wondering, instead of like an op-amp or something like that, well, think about it. If you could use one transistor, imagine the only thing that's limiting... Okay, so I'm going to have to add components to the diagram now. The only thing that's limiting this transistor is, when I say limiting it, I mean it's bandwidth and slew rate. How fast you can switch basically is what I'm trying to get at. It's transition frequency. What's limiting that basically is it's got, well, the characteristics of the transistor itself, obviously. It's a small BC546 at the moment whilst I'm testing stuff because I popped it a few times. It's supposed to be BC550. Now I've got protection diodes in there for the base junction. I will put a 550 in there, but before I had them, I left the 546s in there because I kept popping them. Anyway, so there is a capacitor going from positive to the base. So 10 nanofarad. That's limiting it, obviously. At the moment there's 4 diodes, but I'm going to put 5, so yeah, that's right. Like that. So when a negative spike comes back in the negative terminal, it bypasses the base to emitter reverse junction and doesn't destroy the transistor, breaks it down. That's how I was popping them before, if you're wondering. When I was doing brute force testing, because I've designed protection into the reference circuitry too, so spikes can't damage that, but I was still popping the transistor. So anyway, now I had then, for this driver transistor, geez, I hope this is making more sense than how I normally do it. Please leave feedback for me, because I want to make my videos better. I've only just started doing YouTube fairly recently, so 2 months in, I'm about, so I've got a lot to learn. Anyway, I'm just trying to make this so it's clearer for people to understand. Is that still on camera? Yeah. I just realised I have a smaller work area on screen right now. Okay, so now that we understand the CV circuitry in a crude block diagram, incidentally, there is one other thing I wanted to point out. The reason it gets such good regulation from just one transistor, it's because the biasing resistor for the collector that biases this transistor on, that this one pulls down, it's coming from a regulated supply. It doesn't have to have great accuracy, but decent accuracy is good, over a wide range of input voltages. um, the reference is power, or it's a 0.5% accuracy reference, but it's also powered from a regulated supply I designed myself that, let's just say I can turn the AC input down from 230, 240, 250, whatever the line's at, down all the way to about 185 volts, and it only then drops like a millivolt, if that. So the reference is running off a super stable supply, the comparator transistor is running off a super stable supply, and because the emitter pin isn't just going back to the kappa bank, it's being used to sense. This is a very, very good setup. You'll be quite surprised. And the thing is, using this, all you need to do is temperature compensate this one transistor. And you've got basically something that's almost a voltage reference standard in terms of drift. You know, it can only be as accurate as the reference, obviously, which is made more accurate by, you see, the reference is adjustable, right? So it doesn't matter about the initial accuracy of the reference. It matters about the drift of the reference over temperature, input voltage changes, stuff like that. Now, my reference is also buffered by a transistor on top of that. Then that goes into the pot, and so realistically, this line should be going into the pot, but you get the idea of the principle of operation. Yeah, I put a lot of thought into making a simple circuit that performs exceedingly well in terms of transition speed and accuracy. Just to give you an idea, when it's down the bottom end, when I say the bottom end, I mean 0 to 15 volts-ish, it's about 1 millivolt accurate. You know, like when it's below 10 volts, it doesn't even deflect a millivolt. Maybe even more than that. By the top end, by 30 volts, it's probably about 8 millivolts of error. Like which is, you're not worried about 8 millivolts on a 30 volt rail. You know what I mean? You're worried about 1 millivolt when you're down working on a small thing. This is why I like linear technology. It just works out. You can't beat it. Anyway, so also it's easy to calculate accuracy errors with linear circuitry too, because with using a digital, like a DAC, ADC, stuff like that, your how do I explain this? Your error offset changes as you go up in bits, so it's not always going to be offset by. It's not going to be linear. With something that's linear, you can at least calculate the error out because it's linear. I don't know if that makes sense. For those people who are really, really, really into their numbers and ppms and all that, you'll know what I'm trying to say. Anyway, now the part that I want to talk about is this transistor here. When I keep referring to the comparator transistor or the driver transistor, I'm talking about this here, just for future reference. I don't like calling it the driver. A lot of companies like Agilent, HP back in the day, all those companies called it the driver transistor in their designs. To me, the driver is the one before the output, and the ones before that are buffers, or also parts of the driver. So I like to call this one the comparator because that's what it's doing. You know, it's comparing what's in between its base and its emitter against a reference. It's a comparator. Anyway, we're talking about the comparator transistor. So my comparator transistor initially was hooked up Yeah, I know, if I try and draw a little bit bigger, I'm a lot neater. It's funny that. Also, I find when I start to relax, I have a neater hand too. I'm ADHD, so when I first sit down, I'm sort of, I don't know, I'm a weird person. Anyway, so I had this OR gate. Obviously, one's going to be for CC, one's going to be for CV. That makes sense. And I just add the diodes in. This will all come into play later, so I have to. Okay. When I then took this off and attached it to, you know, this point here, I got a problem. Well, not that point there, the capacitor goes to the base side, so say this point here, right? What happened was I lost AC response because it's a diode. It's only letting current flow one way under DC conditions, and it has some sort of switching characteristics. So although it can let current flow the other way when it's on, it's only when it's on, right? It was causing problems with AC response. So what that means is basically I end up with more noise coming out my series pass element up here. So what I did a whole load of different measurements. I started off with resistors and capacitors. I got down to about 100 to 10 ohms. Sorry, 10 ohms to 1 ohm, and the capacitance I kept going up to about 1 UF. Eventually I ended up deleting the resistor altogether, and I found increasing the capacitance anymore still had no more effect, but deleting the resistor was better. So then I started going down in ESR. So I ended up with a 1 mic MKT across the diode. That worked great. I got my noise back where it needed to be. Now, the more educated of you here might spot the problem. This diode only lets current flow one way in DC conditions. The reference is in anti, it's hooked up in reverse voltage to the base of this transistor. So what starts to happen is this capacitor charges up with the reverse of whatever the reference, the difference between the reference and the output, or reference and the base. It starts to charge up on this capacitor. So what would happen is I'd load my supply with 5 amps, turn it on, voltage would stay there, it wouldn't change. If I tried to charge up a capacitor or something that wanted inrush current, the supply voltage would go down and slowly come back up as if you just turn the supply back on, which I can't have. This is a fast transient response supply. It's got to be bloody as fast as possible. So I said, okay, this is not going to work. I'm going to have to come up with... Oh, and the other thing I noticed too, I don't know if anyone caught this in the last video I uploaded where I was testing the thermals and mounting, or finding out where to put this mean well switcher so it doesn't radiate EMI noise. I didn't realise looking at the panel meter, see, the reason I didn't really pay attention is because the panel meter is not perfectly accurate. I've got to put those 25 turn pots on. These ones are a bit dinky, and I still might have to use a resistor in conjunction with it. I might even end up using resistors, I don't know. But I'm not going to worry about that for now. I've still got some more things to talk about, but I want to talk about this first. Anyway, I noticed that my voltage was at the top end, instead of having like about 8 millivolts of accuracy. It was like 45 millivolts it was drooping at 5 amps. And I go, what the, that wasn't happening before. This thing was microvolts of accuracy down at 3-4 volts, a millivolt of accuracy at 10 volts, and at worst 7-8 millivolts at 30 volts. Pretty accurate supply. I've gone, what the hell? So anyway, turns out it was the diode in the OR gate. So, and no, not from temperature fluctuations. So, incidentally, this 1 UF capacitor solution got the noise down, but never as good as directly connecting this to the base. So I said, okay, I'm going to have to scratch this OR gate idea. So there is still the 103 decoupling capacitor here. 10 nano. I said, I'm going to have to scratch this part of the circuit. I'm going to have to come up with a different way of feeding in the constant voltage signal and the constant current signal to make this transistor pull down the biased on series pass element. I've come up with the idea. We'll get to that in a second. That's why the capacitor's there and the OR gate's there. Alright, now things I want to talk about before I go to that. Power supply's in, noise is okay. Panel meter noise in remote sense. Because I'm still powering it off the negative terminal and the positive's getting powered from a 7812 regulator, it's referenced to negative terminal, kind of, through a bridge, through the main bridge. It's hard to explain. Well, it's not really. It's referenced to one of the windings on the transformer, the 0 volt tap, and then that goes through the bridge, which inherently goes to the output, so that's how it's referenced. It doesn't matter about the voltage being different or anything like that, because it's powering the panel meter and that's got a regulator in it. And no, that's not affecting accuracy. I've tested it off a fixed supply and a supply that changes, and it really doesn't make a difference. The thing that makes a difference is those resistors. Anyway, problem is when you put it in remote sense, you got two 10 ohm resistors there in case your remote sense wires go open. They're probably going to get changed to like 1K or something higher than 10 ohms. I might just leave them at 10 ohms, I'm not sure. So if they're too low, they'll go up in smoke if you disconnect your remote sense and you've got a bit of a load on the supply. That's the only caveat there. Other than that, lower resistance the better, really, in terms of performance. But depending on the resistance of my remote sense wires, when I try and power that panel meter in remote sense mode, it causes so much noise. Actually, let me just turn this thing on. So I gotta wait for it to start up. Like I said, I've got a time delay on it, so that even with the let's get to that in a moment. I don't want to give that away yet. The new drive circuit, that's got nothing to do with the time delay. That's implemented somewhere else. So what was I just saying? Oh yeah, panel meter. I'm not going to worry about this noise. I'll show you the problem I'm talking about, but it's not a problem because when I put, see, some of the other supplies that are going to go in here, including that there, all have isolated outputs because these are flyback converters. So I'm going to have a multitude of isolated supplies I can run the panel meters off, which means basically then I can just reference, I could take, like 100k mega ohm resistor, something insane in value, probably not that high, maybe 10 to 100k, put a cap on the other side going to ground or negative or whatever, filter off the noise, reference that to the negative of my floating supply, put the I can power the panel meter from a floating supply, reference the negative of that with a filter to my remote sense or 2 wire switch negative, and the yellow positive sense wire can just go direct to the positive remote sense 2 wire switch because that never leaks noise into it. It's the current pulses on the negative wire that's the problem. So it's a problem, but it's not a problem because, well, like I said, when I do more work and add more things, I'll be able to resolve the problem then. So I'm just going to leave it for now, but I'll still give you guys a look just quickly. And incidentally, without the Schottky diode in there, you can turn it down lower. And the reason I say this thing will be able to go down to, say, 400 volts, 350, 400 millivolts when it's ovenized is because when you heat a transistor up, it conducts more, right? That's 649 without ovenized. Let's just simulate ovenizing it. You get what I'm saying, right? And it's probably going to be around there. That's why I say 450, 500 millivolts. But that's how low this supply. It's not going to go down to 0 volt because I'm using a single transistor as a comparator, but it'll go down fairly low once it's ovenized. Now, here be the problem. If I go into remote sense, you see that's broken out into oscillation, and look at the screen. I don't think I need to turn the volts per division down. I mean up. I'm sure you can imagine what's there. So, like I said, it's a problem, but it's not a problem because when I have floating supplies in there, I won't be powering them. So the problem is because the panel meter... Oh, I shouldn't have thrown those diagrams out because I've been wanting to explain this better to people for ages, and I just threw out the most relevant bit of paper ever. Sorry. You got to understand, because of this topology, the way it's doing the sensing, and I'll go into how the 4-wire sensing is done soon too. I'm essentially powering my panel meter from here and a plus 12 volt rail, right? And the positive sense is going to here, right? Just imagine that connects to there. And this is the panel meter. It's firing pulses back into the negative sense, into this transistor. That's why it's causing this problem on the output. I hope that makes sense now. When I power the panel meter from just crude, a floating supply, right? Panel meter, floating supply, right? Positive sense wire was never a problem. That can go straight off to positive sense. Negative, might be able to go directly there and not cause trouble. Maybe I might need to put an R and a C like that, and this goes off to maybe negative, maybe earth, some point in the circuit, and then this can go to negative sense. So that's why I'm saying I'm not worried about the panel meter noise. I hope that makes a bit more sense. Why it's a problem now, because I don't have any floating supplies in there, so it's not just measuring across the sense terminals, but it's trying to source its negative current through the negative sense terminal. And just quickly, I'll explain how the negative sense is wired up so it makes sense. Obviously, I've got 4 terminals. Right? The way it works, obviously this goes back off to regulation and ground. The sensing, there's basically a 4-gang switch. So you can think of it as but this is all incorporated into one switch. It's not 2 switches. Okay, that was bad the way I drew that. Right? Then this goes back to the sense positive, this goes back to the sense negative. That way when you flick the switch, which just remember this is a double gang for dual throw switch. So when you flick the switch to 2-wire mode, it effectively just bypasses the 10 ohm resistor and looks just at those terminals. When you put it in 4-wire mode, it's just sensing from the sense terminals, but if you're an idiot and you unplug the sense cables, it'll just sense through the 10 ohm resistor the normal terminals. And there's also a small capacitor, 1 microfarad mono across the 10 ohm resistor, just to help with AC response, because anywhere you add resistance in the feedback circuit that's got some sort of AC response to it, you might want to consider coupling across that resistor with a capacitor that's the right value and a good enough ESR to counteract what coupling you're losing with the resistance, if that makes sense. Anyway, I just threw out, you know, I don't need it again. Sorry guys. I've got too many things on my mind and it's confusing me. Right. So that's the panel meter problem explained in remote sense, and I've shown you guys the capacitor across the OR gate. I've explained why that needed to go. I've explained why the OR gate needed to go. New method with 2 transistors. Let's go do that now. Okay, so I really didn't need that piece of paper. I'm an idiot sometimes. Okay, let's go. What I've done, still got the diodes there to protect this. Got the exact same value compensation capacitor on this second transistor I've added, which is literally in parallel to the first transistor except for its base. The base is lifted. Same capacitor there, so that both same transistors, same comp capacitors, so they're both operating at exactly the same speed, right? Because this is important. At this part of the circuitry, these 2 devices need to operate at the same speed. So, what that allows me to do, where on earth is my lead? Let me just zoom back out. Alright, what that allows me to do, yeah, I'll make up my own leads for everything. Because don't forget, I put the OR gate in there so that one side can go to the constant voltage circuit and one side can go to the constant current circuit. So without that, how am I going to add the constant current circuit? I've got 2 options. I can try and pull current down away from the Darlington array, or I can try and do something here. So I thought, well, where I've got my dropper resistor going to the collector, what if I put another collector of another transistor there, emitter tied to the same spot where it pulls down through this 1K resistor, the Darlington's base, that's biased on via the 47K. So I put my second transistor in there. And I'm going to collect its base to its collector. So as you can see, that pulls it down, but if I turn the voltage up as much as it can go, this is open circuit. It only pulls it down to, say, 11 volts. That's okay, that's okay. You'll see where I'm going with this. Never mind, this is for current limiting anyway, not voltage limiting. Yeah, that's not going to work. I designed these for 4mm spacing. You try and design everything to be fucking industry standard and it still bites you in the ass. Current. So I'll disconnect that collector for a sec. 10 amps. We won't do that too long. Nothing. Turn the voltage up. 1 milliamp, 2 milliamps, 3 milliamps, 4 milliamps. Let's see how much that limits it. Almost as much as the output. Incidentally, that's actually hilarious. It's reading 26 milliamps. Yeah, 26 milliamps, and it's reading 28 millivolts. It's almost bang on for ratio. Only we're not trying to measure current with a panometer. That's why it's funny. Anyways. So, what am I going to do? Well, I think this is a wonderful idea using 2 transistors instead of the diodes, because it allows me to connect this red wire here directly to the base, which solves that noise problem that I was trying to fix with the 1 microfarad capacitor. Solves that problem completely. And the diode OR gate was causing problems with accuracy, and also it's less components, or one less component. Not really, actually, because yeah, it is, because instead of a transistor and 2 diodes, I've only got 2 transistors, so it's one less component. But really, it's a bigger component that's in there, so it's not really. But the beauty of it is it works. I don't have to worry about my noise rejection, my AC coupling, AC response. I'll just use that second transistor to pull it down. So what I'm thinking, this is what we're going to try now, before I wrap up this video, because, well, this is where I'm up to now. So I'm going to perfect this part of the circuit, and then we're going to move on to the next part. That's how this is going. So I'm just going to bring some power here. Got about 0.6 of a volt here. I'm going to put that on the base of this second transistor. Actually, that's what I want to do first. I want to keep looking at current. Incidentally, these cables are fully shielded cables. These are actually, so when I get the rest of my equipment, like 34401As and even more sensitive equipment that I need to take, want to measure right down, that's still set at 30 volts. It's a good thing this is a beast of a supply. There's no current limiting on it. That's why it's a good thing. What? Oh yeah, transistor's not biased off. on. Alright, so I'm just trying a couple of different things. I want to see what happens if I try and bias it against its emitter and its collector and with an external, or should I say not reference voltage, because my constant current circuitry is going to be floating, so there's no reason why I can't use that to bias this second transistor that I've added. So that's, hold on a sec. Yeah, no, adding more voltage here doesn't seem. Yeah, no, that's not going to do anything. Let's unload this for a sec. I'm going to try externally biasing it to its emitter. The only thing is, the emitter is also the emitter of the other transistor, and I don't want to inject noise into that. Whoops. I think I just wired that up the wrong way. Oh no, I got the voltage turned up. I saw 30 volts on the screen. I was like, oh fuck, I just popped it. I've done that before. That's the fun of designing stuff live, right? Sometimes you have to work on stuff when it's switched on, especially when you're designing or repairing something. And a lot of the time that means bang! That just goes with it, you know? The thing is, the trick is to not shy away from those moments. Take it with a grain of salt and keep going. I think too many people get shy. Oh wow, that seems to work really nice. I'm going back up to 30, because obviously I need this to limit all the way up at 30. And yes, the relay system's been designed so that it can't chatter or anything like that. Just don't worry. It's not looking very promising. Might be able to use a MOSFET. I've still got a few ideas. I just wanted to see. What? Oh, I think I've got phantom voltage here. I've just realised what's going on. Hold on a moment. Yep. Okay, so this is annoying. Because if I connect the base of this second transistor that I want to use for the constant current, even just to its collector. Oh no, that is in saturation. No, it can't be. The voltage is the same on the base and the collector. I'm going to go do a little bit of playing around with this off camera because I feel like the video is starting to get too long. But that's where we're at. The switch is in, it's not making noise. Panel meter problem I'm not too worried about because I've got better pots coming for the calibration, plus they're going to run off a floating supply, so that's solved. Thermals are good, and I've just come up with a solution, I think, to get rid of the OR gate that was causing problems. Because what I want to get on with is mounting capacitors off of this board, because I don't know how much ripple rejection it actually needs. A lot of these 3 and these 2 might be able to come out. Not all of them, but most. So yeah. And I also want to get on to making this little ovenized block too. So I'm gonna do a little bit more work on this for now. And I'll come back, make another video when I've come up with a solution to pull this down to at least 1 milliamp, preferably 0. And we'll move on from there. The reason, excuse me, I know why coffee always makes me burp. The reason why I need to work out a way to make the constant current circuitry work before I do the ovenized block is because if that transistor is going to be, actually, you know what? If that transistor ends up being in the feedback loop with the constant current circuitry, it won't need to be thermally, it won't need to be ovenized. I'm going to have to think about this. Yeah, I can't do all this on video. It's going to take way too long. I've got to make some major decisions and do some calculations and work out how I'm going to do this, but I'll upload this and get to work, and then I'll upload the next video. Incidentally, I've got more parts arriving. It'll only be a few days before we're working on the Yamaha amplifier, and plus some of my own builds that are coming up. Amplifier builds, that is. So stay tuned. But yeah, I'm going to leave that here for now. Thanks for watching. I hope you all understand a little bit more of what's going on that I haven't been clear about in previous videos, and please like and subscribe. I'll see you all in the next one. Take care.